Okay, great. Yeah, maybe I can just get started. So I cannot share my videos, but I could just probably make the connection more stable. Yeah. So shall I just start?
Yeah, go ahead.
Okay, great. Yeah, I'm so sorry that it takes a while. Yeah, thank you very much for the introduction, and thank you for the invitation and having me here. Yeah, today, so I'm going to talk about our recent work on synthesizing the dynamic human appearance. So before we get started, I'd like to add a few more words on who am I and what I'm working on. So basically, as Shenju just said, like I graduated from University of Science and Technology China, and then did my PhD in University College London. And I worked in MiHoYo as a research scientist, and then in Adobe research. So my main research area is on digital human. So here we work on both like body movement and also the dynamics of the cloth. We are looking at different poses as well as the motion. So if you concatenate neighboring poses altogether, then it will naturally form the motion. So everything could happen in 2D, like you will see, like we will synthesize the human appearance. But meanwhile, we can do it in 3D so that we will model the dynamic of the mesh, both the body mesh and the cloth mesh, etc. So we were targeting to like realistic appearance, like you do video editing, image manipulation, things like that. And we can also target our method to the virtual character. For example, the character in the game or in some virtual environment. So yeah, so let me first explain our topic today. So we're talking about synthesis dynamic human appearance. A typical problem setup starts from training sequence that's like, for example, someone provided, uploaded, and you can see a girl is dancing. And you would like to learn a character-specific dynamic model to capture the appearance. And during the runtime, you will be provided unseen motion sequence. We can discuss about the representation later, but for now you can see like we can use the 2D skeleton as well as the dense UV coordinate to represent the body movement. And based on the movement, you will influence the character appearance. So yeah, so why dynamic appearance is important when modeling human and what we were motivated. So let's first talk about some high level stuff. Let's see what the like great philosophers says about this. So so here I'd like to quote from Simone de Beauvoir's famous book, The Second Sex. She said, if the toilet has, so here toilet means dress or clothes, or something people wear. So if the toilet has so much importance for many women, it is because they were under the illusion that it provides them both with the world and with their own self. I think this is also true for everyone, like men and women. But let's go back to the graphics and vision world and see what it really means to us. So I'd like to first review what has been done in the 3D side. So at the very beginning, people are stuck with the naked body. In the early work from SMPL, for example, SMPL, like you will see like people build this 3D body model. You provide it with a pose parameter and a shape parameter, then the function will give you the body surface, which capture of course, the pose, but also the shape of the body. So later on, we extend the approach to some to include some tight cloths. So in Cape, you can see like we use one hot vector to categorize the information about cloth, the type of cloth and the shape of cloth, the tightness, things like that. And with the parameters, you can model the human with tight cloth. One issue that here preventing us from extending it to some loose cloth is most of this approach are modeling the cloth surface as a displacement from tight body, so it cannot work with different topology as well as a very loose cloth that the vertices are far from the body itself. So moving towards the next step, we can do the loose cloth. So in this scale paper, what they do is they predict the position of the cloth in 3D, of course, based on the given pose, and then calculate some neural feature for the vertices, and then synthesize the geometry and appearance, etc. But so for now, everything is in the pose space. So everything, all the appearances are pose dependent. Here we show examples to compare the difference between the pose-dependent appearance and motion-dependent appearance. As you can see, for pose-dependent appearance, what is really important is just the current frame, that you can infer almost everything from the current pose. But in many real-life scenarios, the appearance is not only related to the current pose. It's also related to the sequence that get into that pose. For example, if you are wearing some very loose cloth and doing some movement or have some interaction, say if you touch your cloth with your hands, something like that, so you will change the shape, and then everything is in dynamic. So following this principle, there were also some work trying to address the modeling of the human in motion-based appearance. So in this Synthesizing work, it try to model the deformation of the cloth given the body movement. But this area is still not very well explored area. So there are a lot of strong limitations. For example, the type of cloth is fixed. It can only infer the coarse shape, but not physically correct geometry details. It can only work with some very simple body movement. They are mostly captured in the lab environment. So yeah, so in the 2D domain, like people first try to propose some very general image translation based method. So basically, they train a generative adversarial network that goes from one domain to another. Yeah, so the method is not human specific. It can work with any domain, but you can imagine when applied to our scenario, the left side can be the image for a 2D human pose, and the right side can be the target appearance of the character. Yeah, so later on, everybody dance network, people try to use a human-specific setup, and also try to add some temporal coherence to improve the performance. But as you can see from the example here, they can only work with tight cloth and also the pose-dependent appearance. So last year, Couple et al. Proposed this neural human approach that for the first time can work with loose cloth and deal with the motion-dependent appearance. But there are also very strong limitations. As you can see, they first use some structural regularization to improve the quality for loose cloths and texture synthesis. But it turns out the structure itself is very difficult to generate, and and also the dynamic of this structure is very difficult to learn. So to summarize, the difficulty of the limitation of the existing work in this topic is listed as below. So one thing is about the data issue. Most of this approach needs about maybe 20 more minutes of recording and learn from them. Some of them are even from the multi-view data input. So that makes the methods not really practical in real world life. Another issue is about the motion dependency. So some of them are recurrent based approach. So the error will be accumulated during the process. Another issue, which is quite obvious, is the low synthesis quality. Most of them have poor performance on fast movement, and also the fine texture, and also the scene structure. Scene structure, I mean, for example, the hand, fingers, or the hair, things like that. And last but not least is the 3D ambiguity. So this is an interesting problem because the character is moving in the 3D world, but all we're doing is in the 2D projection space. So that means there will be some depth ambiguity, especially when the people are doing some like 3D rotations, things like that. So they will be very difficult for a 2D based approach to capture and synthesize this type of scenarios. So the first work I'd like to talk about is our 3D vision paper last year called Dancing the Wild, a monocular human animation with neurodynamic appearance synthesis. So in this work, just like recall what we have discussed previously about the problem setup. The input is the target pose or motion representation, and the output is we want to synthesize the possible 2D appearance. There are two stages here. One is about training. So during training, you have the supervision from your data set, which is a video sequence. So it's mostly a reconstruction task. I try to reconstruct the possible appearance. The second stage is during the runtime. It works as retargeting. For example, you will generate the video animation for the unseen sequence. So let's look at some data that's captured from social media, and we can have some better understanding of what's the problem we're facing at. So one thing we can observe is people love to dance and love to capture themselves dancing. So, but usually they wear loose clothes, and clothes sometimes with very complicated texture. And people tend to do like interesting movement, which is usually complicated and fast. And in some cases, they have long hair and very complicated hairstyle. And also for the duration, there are really limited data sets because most of them are within 3 minutes. And it won't be realistic to expect someone to upload a video that captures him or herself dancing for like 20 minutes. So to address the above issues, we propose this StarGAN-based network. So let's look at our architecture. We have two branches here. For one branch, like we do the pose information. So starting from the pose representation, which is the dense UV and the 2D skeleton, we train a network to extract the pose feature. And on the other branch, we concatenate the poses from the past frames to form the motion feature. And we train a StarGAN generator that start from the pose feature, but modulated with the motion, learned motion feature, which can then generate the target image, which is based on the target pose, but also be aware of the motion that formed this pose. And so we trained our network with very typical reconstruction loss and perceptual loss. And we also add the adversarial loss with the discriminator here. So one thing makes the problem a bit difficult is the temporal coherence of the pose prediction. So as you can see here, actually it's a small video playing and the character is standing still. But you can see the dense pose prediction as well as the 2D skeleton prediction is not quite stable. There are some artifacts, there are some jittering, and some of the body parts are missing or flipping. So yeah, so single frame pose detection is always imperfect. So to address this issue, we not only use the learned motion to modulate the generator, but also we use that to refine the learned pose feature. So by doing that, we hope that the error can be averaged from the information, using the information from the past frames. So here are some results. As you can see, that our method can synthesize plausible appearance as well as the dynamic shape. Here you can see for the upper right example, you can see we not only synthesize the fine wrinkles, but also the shadows. And of course, for the checkerboard texture pattern, as well as the text texture pattern. So in terms of the application, one thing we can do is for the retargeting. Here, we train the network with different we train different networks from the different input video, and during the runtime we just feed them with the same target motion. So you can see the dynamic appearance is synthesized, and the movement are synchronized as well. So yeah, now let's look at the comparison. Our method, so here's the comparison between our method and other state-of-the-art approaches. As you can see, for the texture detail, sorry, for the details, for example, the face detail and hand detail, and also for the texture, like the dot patterns and the text patterns here, and as well as the overall body shape. Ours achieves the best among the other competitors. So here is the experiment to see how the refinement helps for the pose detection. So given the target input pose, the vanilla result means that we just directly generate the results using the input pose. And for ours, as you may remember, that we use the motion feature to refine the pose feature learned from the upper branch. And so you can see that for the vanilla one, you can see some jittering of the appearance. So I'm not sure if the screen sharing can show this, but at least from my side, I can see that there are some jittering in between the neighboring frames. So for the mid column, we also compare it with some smoothing method, like applying Savasky-Golay filter over the feature domain. So you will smooth the learned feature. So the good thing is it indeed makes the output more smoothing. There's no jittering anymore, but it also plays pretty bad on the fine details like the hands and the hair. So you can see from time to time, the hand is really off because the features are averaged. So let's look at the numbers. Here we achieved the state-of-the-art performance among the most commonly used metrics. And one thing to be noticed here is we also compare this optical flow error. So what we do is we compute the optical flow between the neighboring frames. So that can highlight the problem of jittering, because imagine if the frame is jittering, the overall shape might still look similar, but the optical flow of the neighboring frame will be significantly affected. So we show two examples here. For the ground truth or optical flow and our optical flow is still quite similar, but for the vanilla one, you can see the jittering caused a big issue here. The overall, you can see there's some global transition in the image domain to that then makes the optical flow looks very different. Another thing to look at is motion pose disentanglement. So here we have two branches. One is for pose, one is for motion. That means we can synthesize the same pose with different motion that leads to this pose. One very simple but interesting test is we can play the video forward and backward. So as you can see here, for the first column, we show the ground truth image. So actually the girl is actually moving towards her right side. So the cloth is dragged a bit left. If we play the video, so if we fit the network with forward motion, which is actually play it in the normal direction, you will see that we synthesize the cloth. The cloth we synthesize is also a bit dragged to the left. So if we freeze the motion, which means we just use the same pose feature, same pose input for all the past frames, and so you can imagine actually the character stands still for the same pose for a while. You see that the cloths are dragged naturally. And if we play the motion in the inverse order, like use the pose from the future frames to form the motion sequence, you will see that like the cloth are the dress are dragged a little bit to right. So here we ask the question that what when we do this motion feature, what's a good duration for the motion should be considered. So we did several experiments and find that like 20 frames is a reasonable estimation. So here our frame rate is about 16 FPS, which means the past 1.5 seconds is quite critical to understand the dynamic appearance. And this agrees with our like intuition on the data capturing. So here we also review the limitations I brought up previously. So about the data issue, previously we need 20 minutes of recording, but now like only 3 minutes is quite enough. And for the motion dependency issue, it's gone now because we're using a fixed length of motion window. And for the quality, we can work with almost any type of cloth, any type of body movements, and of course, under unconstrained capture environment. So as long as the movement is as long as like this is a normal movement, then we can do it, but not a crazy movement. Later, I'll explain what crazy movement is. So the last part is about 3D ambiguity. So this is something we're still missing. The solution here is we should use more 3D signals, as well as putting everything into the canonical domain so that we can learn the feature more efficiently. That leads to our recent CVPR work on this motion-dependent appearance synthesis. So in this work, we mostly ask the question that how to effectively learn this body motion. Effectively learn this body motion features so that we can model how the garments would react to this. So starting from the 3D body movement, what we can do is, because this is a simple body, right? So we know the parameterization, so we can just project everything into the parameter domain, and we can calculate the normal of each vertices, and then copy it to the UV domain and the velocity as well. And if we concatenate all the layers together, and pass it through a neural network, it will give us a feature map here in the UV domain as well. And we can copy each pixel back to the image domain to project it over the surface of the moving character. So in that way, we have a per frame feature in the image space. And then a neural network will help us to synthesize the final appearance. So just give more details here. Instead of directly working on the final RGB appearance, we're also having the body parsing as well as the normal map synthesized at the same time. And we find that having this like side task also helps us to learn a better appearance synthesis, especially for the challenging cases with 3D rotation. So one question to ask here is how we can get high quality 3D body sequence. As you can see here, for the given video sequence, if we just run some state-of-the-art method, it's not the result is not great. As you can see, like the boundary is slightly off, and also the face is not perfectly aligned, and of course the detected character is also jittery. So for what we do here is we can train a network to predict the camera parameters and also the pose parameters. And we ask the parameters not to change dramatically during the sequence, and also close to the prediction from the state-of-the-art method. And we can, since we know all the parameters, we can actually generate the mesh and do some differentiable rendering to get the UV coordinates, and we can compare it with the dense UV detected by the other methods like dense pulse. And so we can do this in per pixel wise, and also we can do this in like per vertex wise. So after this refinement, you can see that our result is getting much better now. So here we show some our final results. As application, since this time we have the novel view, this time we have the 3D information, so we can do the novel view synthesize. Yeah, so you can see here, if the character is rotating or slightly changing the view direction, it will be very easy for us to synthesize the new appearance. Also, the normal could help us with the relighting. Yeah, so of course there's no like self shadow here because we're only using the normal map for relighted image. And last but not least, this motion retargeting. So this is a very typical application. So one experiment to show here is we use a reduced amount of training data to train our both this method and the previous done in the wild work. So this is a very interesting experiment, as you can see here, with the limit when the amount of data is reducing, the performance of this work is not reducing. This it's not it's still trying to keep a very good performance. So that is partially because the normal and the velocity information is very intrinsic and help us to learn the representation more efficiently. So now we can let's review the limitations listed above. So here we reduced the data usage, and it's not motion dependent. It's not dependent on very long motion sequence. And also for the synthesis quality, it's good now. And we can also address the 3D ambiguity using the normal and the velocity information. So in terms of the conclusion, the first thing is we can use StyGAN to generate the plausible appearance from the pulse and also modulate with motion. And we can use motion to refine the unstable pulse detection. And the last thing is we can use some 3D information to represent the character, and which is also very efficient for us to learn in the 2D synthesis task. So for the ongoing and future work, one thing is very interesting here is about the generalization to extreme pulse and motion. So this is the crazy movement I was talking about. So here's an example. If you find some like image from the web from the internet and you extract the pulse, and this is not really covered from the data set that we train the network. So the synthesis is like it's good everywhere, but like for the lag splitting part, there are a lot of artifacts. And then on the right side we show the nearest neighbor from our train set. Here, so how we address this issue? The basic idea is to borrow some physics constraint here. If we review what people has been done in the game industry, that people will use a skin bone structure. So instead of running the physics simulation for all the vertices of the character, it just simulates the dynamic of the bones and using the skin weights to recover the whole surface. Like here, we probably can borrow some similar idea here. Say we we embed some like neural bones here and try to learn the dynamic of the neural bones. And such dynamic should subject to some physics constraints. And we only use a neural network to synthesize the detail appearance so that the overall shape will not go crazy for the unseen pose and motion. Another topic to explore further is about a better 2D representation. So as you may see, like for both of the work, we're using a dense pose to get the 2D appearance, to get the dense 2D UV coordinate, but this is not perfect. There are a lot of issues. For example, the silhouette is not correct. The layered information, there's completely no layered information, and also the details, for example, the wrinkles and maybe the hair is not well captured. So how to train the model that can give you such detailed information is also very critical to make the network being able to capture the fine detail, the information. Yeah, just trying to say that the 3D post information is quite important for you to address the 3D ambiguity, for example, the 3D rotation. So that is also something we're investing for now. So yeah, that's actually basically my my talk. But before I finish, I'd like to quickly talk about Adobe Research London. So we're growing, and we have amazing researchers, and also we're working on very interesting problems. There are full-time positions and also research intern positions open, so feel free to reach out if you're interested. And yeah, thank you very much. I'm really sorry for the connection issues, but yeah, glad we have make it.
It's okay. Thanks for the nice talk. Well, actually, there are many amazing results. So, is there any question from our audience? So maybe let me ask first. Actually, I have some questions about your second work.
Mm-hmm.
Well, my first question is that I'm wondering if your network is subject specific. So I mean,
It is, yeah.
Oh, so once the network is trained, it can only handle this particular character, right?
Yeah, for both works, they were character specific.
Oh yeah. So do you have any ideas about how to extend the current approach to be a universal one? Do you have some ideas?
Yeah, I think it's definitely a very good question. So so for now, most of the appearance synthesis is character specific. Training the network from scratch takes a very long time. For example, for both the work probably take like 1 day or 2 days to make the network converge. So, but the good news is we can refine it. For example, if you train the network for one character, and you can refine the network for another character. We did some quick experiment, and it turns out like maybe just like 10 to 20 minutes, it should be quite enough for the network to converge. So that is how we deal with the efficiency issue at this stage. In order to have a general method, so that probably involves adding another appearance feature. So instead of doing pose and motion, we also need to add appearance. So for example, imagine you have the StyleGAN, right? So you can first embed an image into the StyleGAN space. So you will learn a latent code for that image that will capture the appearance of the character. And then we can feed this feature into the network in some way, and then the network will know that whom to synthesize. But that can be very difficult because the appearance of the character is can be very different. Like the texture variation, the class variation is quite significant. Training a network efficiently, training a network for this efficiently can be a really interesting but challenging research direction.
Okay. Actually, I'm not very familiar with your topic. So the input of your method is a sequence of images, is a video, right?
Yes.
So does the background in the video affect the final result? I mean, if the background is very complicated, or it's raining or it's foggy, so will this affect the final result?
Yeah. So of course you can do the background segmentation, right? You can just work on the foreground. You can definitely do that. But in order to do a good synthesis quality, we can include the background as well. The only issue is from the background, you can know more information about the character, right? You can know like what's the camera view, like it's like pointing down or point in a horizontal way. And you can also know if the camera is moving. Because, for example, if you completely mask out the background, you see the character is moving in this way. It's probably the character is moving, but it's also probably the camera is moving. So with the background, you can efficiently capture this type of information and compensate that in the character space. So you will not like put the camera movement onto the character body, so the dynamic can be more accurate. Yeah, so I think that is the difference between having a background or not.
Okay. Well, maybe let me ask one more question. So if the body is moving very fast, for example, the fast movement of our hand region may be blurred in the video. So in this case, how about the performance?
Yeah, so motion blur is always a very difficult thing to address. It's so mostly it's the noise in the training data, because for such frames, the supervision will be noisy and will not give you a very accurate guidance for the appearance. But I guess that is all, because during the runtime, you will directly start from the post sequence, right? So for the post detection, the motion blur is not a very significant issue. And I believe, so at least for now, we're mostly using the per frame post detection, but I believe there are some ongoing work that trying to use some temporal information to make the post detection more reliable or more stable. And if that is this type of work is accessible, then I guess the quality of the post estimation can also improve, and the motion blur will not affect at all. So yeah, it's basically the noise in the training set.
Okay, I see. So if there is no further question, so I think that should be all for today's talk. Thank you again
very much
for the sharing.
Yeah.
So thank you for the audience for attending this session. So that's all for today.
Yep.
See you. Bye.
See you. Bye-bye.